So yesterday we talked about rational functions and the good things that go with that. Starting that process, okay? Zeros. What do I need to do to find my zeros of this function? Factor, okay? Factoring's been our friend, and it's going to continue to be so. It might be your enemy, I'm not sure, but we're going to factor. Let's see, so what, x minus 7x plus 1 on the numerator. The denominator, does it factor? No. So we're going to leave that bad boy. All right. Where do zeros come from in a rational function? The numerator. Okay. So we're only going to look at the numerator. So x minus 7 equals 0, or x is 7. And then x plus 1 equals 0, or x is negative 1. Okay. So those were our zeros. Yesterday we talked about end behavior. And when we discuss end behavior, there's 3 options. Okay. There's 3 options. And it all deals with the highest degree terms of the numerator and denominator. And so if we look at those, x squared over x squared, they match. Okay. So am I going to have a horizontal asymptote? It didn't ask me, but are we? Yes. And it's going to happen at y equals what? 1. Okay. X squared over x squared would reduce to 1. And so our end behavior is also going to approach that asymptote. So the limit as x approaches negative infinity of f of x would be positive 1, and the limit as x approaches positive infinity of f of x would equal 1. So that's what we talked about yesterday. Okay, and we also solved those nasty rational inequalities. Those are gross. Right. All right, do you have any questions out of your lesson practice from yesterday? I was going to work some of those if you needed me to, but if you don't, that's cool. Okay. Isaac, I went home last night, like when there was a minute and some odd left of the game. Yeah, I had to go. Well, actually, I blamed my husband. It was about 4 minutes left. You know, when we kind of had that rally in the fourth quarter, he'd gone to the bathroom, and then he came back, and we weren't rallying anymore. I said, I'm about to have to send you back to the bathroom. Like, he goes, that's it. I'm going to the car. So when they went up on like past 6 on us, he said, that's it. I'm going to the car. And I was like, okay, I'm coming. So he was like, I can't be blamed for this. I'm like, oh, my God. You have nothing to do with whether we win or lose a basketball game, but that's okay. God bless him. All right. He coached baseball just long enough to be superstitious. So, you know, you don't mess with a streak. That's the rule at our house. Okay. All right, so no questions out of your lesson practice from yesterday. Well, all right, then let's jump in here and let's get after today's lesson. So we're going to still talk about rational functions today. But today we're going to address vertical asymptotes. So yesterday we talked about horizontal asymptotes and holes in a function. Yep, functions can have holes. It's really weird. Okay, you can be going right along, whoop, there's a hole, then it keeps on going. Like, it's just weird. It happens. So that's what we're going to discuss today. All right. So let's get into what is a vertical asymptote. Well, we know it's a vertical line. Okay. But basically, a vertical asymptote are factors of the denominator that do not reduce with the numerator. So factoring again, I can tell is going to be important today. All right. And we basically take those parentheses and we solve for x. Okay, so whatever's left in the denominator, we get a vertical asymptote. It is an equation. Okay, x equals a. Interesting thing about it, basically these are the things that would make my paper explode. Okay, where the denominator would equal 0. So they're the things that would make my paper explode. They cause my function to be undefined. So just like horizontal asymptotes where y equals some number, vertical asymptotes are x equals. If you just put 3, I will back it wrong. Okay, it's x equals 3. So we want to be sure it's a linear equation. We want to write it as such. Now, a hole. How do we get a hole in the graph? All right. Well, remember yesterday I talked about where those factors repeat from numerator and denominator, and that's where our holes happen. Okay, they're going to happen where factors repeat in the numerator and denominator. So, Elise, what do y'all do when y'all go to the middle schools? You just talk to them about.
So there's different categories.
Mm-hmm.
So I'm kind of in the script part. So you have a little play kind of act.
Okay.
Kind of showing drug prevention, that kind of thing.
Okay.
And last time it was about peer pressure. But then they also have they have drug driving goggles type things they do, parts and stuff.
Okay.
Just stuff like that.
Okay, cool. That sounds fun. All right, so let's take a look at some rational equations or rational functions. And let's see if we can figure out if they have a vertical asymptote, do they have a hole, do they have both, what's going on in these functions. All right, so let's take a look at the first one. All right, so we're looking for factors for vertical asymptotes, factors of the denominator that do not repeat or reduce, and then holes if I have a factor that repeats. So if we look, is that the cow or the bear? That's the cow. You can't trust a cow. All right, grass puppies. That's what we call the little bitty ones, the little cows that you can get, the miniature ones in your backyard. Yeah, too much poop. We call them grass puppies, though, at my house. My husband really wants one, and I'm like, no. Just because our Pitty has cattle dog in him, so he likes to herd people. We would prefer him to herd an animal over us, but anyway. Okay. All right, so let's look at the first one. So x minus 1 times x plus 2 over x minus 1. Which situation do we have here? We've got a hole, all right? We have a repeated factor in the numerator and the denominator. So we're going to have a hole at x equals positive 1. It's always the opposite of the number that's in there. Okay, so we have a hole. Let's look at the one next to it. Okay, do I have any holes in that one? No. Okay, so I do have a denominator, which means we're going to have a vertical asymptote. And my vertical asymptote is going to be x equals 1. Okay, so in the first one I had a hole when x was equal to 1, but on the second one I actually have a vertical asymptote. So if we graphed it at 1, the function would be undefined. We would put a vertical line in that's a dotted line. Okay, now the next two are really interesting, I think, because we've got to do some reducing to figure out what situation we have. Okay, so let's look. I have x minus 1 cubed, and on the bottom I have x minus 1 squared. All right, if we reduced those two terms, okay, what would happen? If I have something cubed on the top and something squared on the bottom. I get left with just one of those in the numerator, right? These exponents would subtract 3 minus 1, so that one's going to be gone, would leave me to the first. Okay, so when I look at this picture, okay, because I'm left with 1 in the numerator, it's not in the denominator, we actually have the hole. Okay, we have the hole at x equals 1, right, because it repeated. Right, it repeated, but I was left with 1 in the numerator. Okay. If we look at the second one, I have x minus 1 over x minus 1 squared. What's going to happen when I reduce those? I get 1 left in the denominator. And so if it's left in the denominator, it's a vertical asymptote. Okay, so you might make a note to yourself there, all right? When we reduce, if it's left in numerator, it's a whole. If it's left in the denominator, it's a vertical asymptote, okay? So after we reduce, that's how we can tell the difference between the two, right, in terms of what we have. Okay, question on that? All right, so repeated factors give me a whole. Things left in the denominator give me vertical asymptotes. All right, Roderick. All right, so let's flip it over and let's look at what comes next. Let's take a look at this graph, okay? And let's just talk about what we see. What are all the unique things that we see in this graph? These graphs look pretty similar, all right? Does this graph have asymptotes? Sure does. We got dotted lines, we got asymptotes, all right? What's the one that goes across? What do we call that one? That's a horizontal asymptote, okay? It's a y equals equation, and where does it go across at? 2, okay? So I have a horizontal asymptote at y equals 2, all right? Do we have a vertical asymptote? Where does it go across? -1, so x equals -1, okay? Do we have a hole in this graph? Okay, not a trick question. Is there an empty circle somewhere in the graph? Yeah, okay, that's a hole. What x value does it occur at? At x equals 1, okay? So that's what a hole looks like when you graph it. Now, on your calculator, it's very difficult to see a hole because of the pixels in the screen, all right? So it's hard to see those. So a lot of times we have to look at a table to know that it's undefined there, okay? Now, what about the second one? All right. Does it have a horizontal asymptote? Yep. What's its equation? Y equals 1. Does it have a vertical asymptote? What's its equation? X equals 1. Does it have a hole? I don't see any. Okay. You'll be able to see them if they give you a graph. It's an open circle, right? Now, one of the things that we've got to talk about today is how to describe behavior, and this should say around vertical asymptotes, okay? So add that in right there, okay? I want to talk about how do we describe the behavior of my function around a vertical asymptote, right? To the left of that asymptote and to the right of that asymptote. Okay, so to the left and to the right. The thing about vertical asymptotes is that it's either going to approach positive infinity around it or it's going to approach negative infinity, all right? So if we look at the two graphs that we have right there, all right, around that vertical asymptote, it's either going to go down or it's going to go up, okay? So to the left and to the right of our vertical asymptote. So we're going to use limits, all right? Now, here's the thing. As x approaches a, and I'm going to put a little negative up there, okay? If you had to guess, that a is the vertical asymptote itself, okay? If you had to guess, which side would you think I'm talking about when I put the little negative up there? The left side or the right side? The left side, okay? That's what that means, okay? So the limit as x approaches a from the left of my function is either going to go to positive or negative infinity, okay? So this would mean from the left. If we want to do the right side of the asymptote, limit as x approaches whatever number the asymptote's at, and we put a plus sign like in the exponent spot. That means from the right, okay, of my function. And it's either going to go up or down, all right? It's going to point up or it's going to point down. This is my from the right. Okay? So we're going to use limits again. Okay, but we're not going to approach, okay, x isn't going to approach positive and negative infinity. It's going to approach a number from the left or the right. It's where that vertical asymptote is, so that's the difference, okay? When I have a graph, it's easy to see. I can look at it, all right? On the left side, is the graph going down next to the asymptote, or is it going up? On the right side, is it going down or is it going up, all right? When I don't have a graph, all right, when I don't have a graph, we have to check numbers around that asymptote, okay? We're going to plug in some x values that are really close. So if it's at, let's say, positive 1, I might check 0.9 and 1.1 or something like that, okay? Something close. You don't want to get too far away because graphs do weird things as we get farther away, all right? If I get a positive number, it's approaching positive infinity. If I get a negative number, it approaches negative infinity. So make a note to yourself. If it's an equation only, we're going to check values close to the asymptote. Okay? If it's positive infinity. If it's negative infinity. And we're going to do both. Okay? So let's go back to that first graph, okay? And let's do the limit statements based on the graph, okay? For my vertical asymptote. What's it doing around that asymptote? Well, you told me that my asymptote was at x equals negative 1, okay? So my two limits are going to be this. The limit as x approaches negative 1 from the left, and the limit as x approaches negative 1 from the right, so with the plus sign. Okay, so those are going to be my two limits. The asymptote's at 1. I'm going to look at the left side of the asymptote and the right side of the asymptote. All right, so those are going to be my limits to start. Those limits are always going to equal either positive or negative infinity. Just depends on which way it looks, okay? So let's go over here and let's look on the left side of the asymptote. Okay, so here's my asymptote. On the left side, which way is it going as it gets close to the asymptote? It's going down, so I would put negative infinity. Okay, so as I get close to that asymptote on the left side, all right? Now let's get close to the asymptote on the right side, all right? Which way is the graph going? Positive infinity, it's going up, okay? So that would be my description of the behavior, okay? So you're getting close to the asymptote, all right? Getting close to it on the left side, getting close on the right, all right? See if you can write the limit statements for the second graph. All right. Where's my vertical asymptote at? 1. So we're going to do the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. So we'll use the minus and the plus. Okay. Which way is it going as I go to the asymptote from the left? Negative infinity. And which way is it going as I get close on the right? Positive infinity. Okay? So question about those limits, writing those. Okay? Because that's different from when we're doing in behavior. Okay? In behavior. All right. See if you can do these first 3 on example 1. Okay? All it wants you to do is to give the x values of any holes and the equations of any vertical asymptotes. All right? So take a second. See if you can do those first 3, A, B, and C. Bless you. Carla, you got to work till 9. It'll be okay. Spend the big bucks. Okay. Kevin, did you go to track practice yesterday? I saw y'all down there running. Yeah, I never run on purpose, just so everybody knows. If you catch me running, you better call 911 because someone's chasing me. Or there's an ice cream truck nearby. So, I do love ice cream. You know. Or tacos. Okay. So let's look at the first one. X minus 2, x plus 3, x plus 3, x minus 5. Do I have a vertical asymptote on this one? What is it? X equals 5. All right. Do we have a hole at this one, on this one? Yep, I've got a repeated factor right there. So it's going to happen when x is negative 3. So I had a vertical asymptote and I had a hole on that one. Okay. All right, let's look at the next one. Do we have a vertical asymptote? Okay, yes. I noticed I got 2 repeated factors here. Okay, which one's going to give me the vertical asymptote? The x plus 1s, right? Because it's going to reduce and leave it in the denominator. So I'm going to have a vertical asymptote at -1. Okay. Are we going to have a whole? Yes. If we reduce the x minus 2's, it's going to leave me with 1 in the numerator. So that means it's a whole. So at x equals 2. Okay. So if it's left in the numerator, it's a whole. If it's left in the denominator, it's a vertical asymptote. All right. So we want to be sure that we're checking those. All right. Now, what about the last one? Could we approach that one just like we did everything else? What do we need to do with that one? Factor it first, okay? We need to factor it first, right? And so if we're going to factor it first, what do we get when we factor it? Dun, dun, dun. You don't have to quit talking because Dr. Becker walked in. All right, for x cubed and 4x, so x times, let's see. What did you factor out to start with? An x, and it left you with x squared plus 4, okay? Now, can we factor that x squared plus 4? Okay, you say yes, I heard a no, all right? Why do you say no? It would give me a negative in the middle, so it's got to be a negative. That's a real common mistake. I'm glad you said that. Okay? Yes, it has to be that x squared minus 4. It's got to be the difference of 2 perfect squares. Okay? So, pretty common mistake that will happen right there. All right? So, do we have vertical asymptotes on this one? Okay. Where are we going to get a vertical asymptote? Y'all are cracking me up. Okay. So we got, what are our options? How many factors do we have in the denominator? We got 2. Okay. And just like we did for the rest, let's set them equal to 0. Okay. So the first one's pretty simple. X equals 0. That's definitely going to be our vertical asymptote. But what's going to happen if we solve for x in that second one? Yeah, we're going to get a complex number. We get an imaginary number, right? We pull that 4 over. That would give me x squared equals -4. That would be square root of -4, which we know gives us that plus or minus 2i. Can we see complex or imaginary numbers on the coordinate plane? No, so we're not going to see that asymptote there. All right, we're not going to see it. So that's not going to be 1. So anytime that happens, you can disregard it. All right, you don't need it. Do we have any holes on this one? No. All right, we don't have any repeated factors, so we would say none. Okay, which is nice. All right. What questions do you have about that? Just be careful with your factoring. All right, be careful with your factoring. Okay. All right, let's look at the next one. So it says, describe the behavior around any asymptotes using limits. Here we go. All right, so if we're going to use limits to describe behavior around my asymptotes, we did that a few minutes ago looking at a graph. This is the first ones we've looked at that actually have an equation. So first thing, do we have a vertical asymptote? Okay, at least where's the vertical asymptote on this one? At x equals 2. Okay, my vertical asymptote is at x equals 2. All right, so if we're going to describe the behavior around that asymptote, how many limits is it going to take? It takes 2. Okay, so the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Okay, now, how are we going to figure that out? We don't have a graph. Okay, this was where I talked about that we might have to check some values. Okay, yesterday when we were solving those inequalities, those rational inequalities, we used a sign chart. Okay, we're going to kind of do the same thing. All right, thinking about it. So let's think about our asymptote, it's at 2, all right? Let's pick a number to the left of 2 that's pretty close to 2, all right? What might be a good number? Okay, we could pick 0, but honestly, that's probably a little too far away, all right? So 1, or even better, would be like 1.5, 1.8, 1.9, because we're just trying to figure out the sign. Is it positive or negative? Okay, so let's think about if I used 1.9. Okay, that's definitely to the left, all right? If we plug 1.9 into that equation, let's talk about what's going to happen, all right, to the signs in our parentheses and what would happen, okay? So if I plug it in, 1.9 minus 1, would that give me a positive or a negative? A positive. 1.9 plus 3, positive or a negative? Positive. Oops. Get my pencil back. And then 1.9 minus 2. That would give me a negative. All right? So if I take a positive times a positive, I divide it by a negative, what do I get? I get a negative. So guess which infinity we're going to approach? Negative infinity. And that's what we're going to do. Okay? So those sign charts are good for that, for us just to kind of think about the math, what's happening to those y values around that asymptote. Okay? Let's do it on the right side. Okay? Good number close to 2. 2.1. All right? We want to keep it close. We don't want to get too far away. When we're solving inequalities, using a 0 is helpful. All right? In those regions, it makes our math a little bit easier. But for this, we want to be really close. Okay, so 2.1 minus 1, what's that going to give me, positive or negative? Positive. Okay, 2.1 plus 3, positive. I'm going to divide it by 2.1 minus 2. All right, positive times a positive divided by a positive, I get to stay positive, and that gives me positive infinity. Okay, so let me stop right there. Question about that. We did a lot of mental math right there. Okay. Checking that behavior around that asymptote, right? And if you didn't believe me, could we put it in the calculator and look at it? All right, let's do that, all right? Let's just make sure that we're correct. Let's put it in there because, I could lie to y'all. I've done worse things, all right? So grab your calculator. If you want to use your app on your iPad, that's fine with me too, all right? Let's put that equation in and let's look at it, all right? We may not see the asymptote, but we should see the behavior around it. Okay. Did y'all look like that? You may see more because your window's a little different than mine. Okay. Well, I can definitely see that it's on at 2 where we thought it was, right? That on the left side of 2, it's going down. What's the problem with the other side? Yeah, I can't see it. Okay. So that means we got to mess with our window. All right. We got to mess with our window. What part do we need to see more of that picture? Up, down, left, right. Yeah, I need to go up a little bit, okay? So, because we're worried about what's happening around 2, so I think my X's are fine. Let's go into our window and let's adjust our Y's. So jump down here to your Y max, and let's clear that out, and let's put, I don't know, 25, 50, something. I am going to change my scale. Or it's already at 10. I don't want a fat axis, so I'm going to leave it at 10. Okay? And I hit graph. Can we see it? There it is. All right, so we can definitely see around 2 we were doing the right thing. All right, so that's why we check those y values of the function to know what's happening. Okay, question about that? All right, y'all try that next example. All right, try that next one. What are your asymptotes or asymptotes and the behavior around them? Let's see how we do with that one. different than the last one? How's it different? Oh, we've got two asymptotes. Okay, we've got two asymptotes. So we're gonna have to do it for both. You can go. It's my bottom drawer and all of my pins, so that when I'm sitting at my desk and I need to work, I can, I need all the colors, all the pins. Yes. And if you act ugly, I'll hand you a finger.
No, you can keep that. Straight up.
Okay, so think numbers. So if I have negative 2 times negative 2, that'd be positive 4. Divided by positive 2, that would give me a positive answer. So positive divided by positive. So we're just thinking about normal. What is happening? There's too many words. Yeah, we did a problem in calculus today where like you do all these words, but process is so simple. They're like, there's so many words. And I'm like, and they're big math tests. So, yes, I agree. It's a lot. Okay. Building your castle. Y'all crack me up. If I ever put real Legos in those baskets, we never get anything done.
I don't know what you mean.
But every adult that comes in goes, "Oh, you have toys." Every grown person. It's so funny. I came in here, they were having a workshop in here, a PD or something. Teachers from other schools, every last one of them had something in their hand, messing with it. And I just started giggling. I was like, y'all are worse than children. Teachers are a bad audience too, by the way. We're terrible listeners. We can't help it. All right, so let's dig into this one. Did you get it? Yeah. I could tell that was a sound of victory over there. All right, so when we look at this one, we notice that there's that x minus 2 that's going to repeat, okay? And when we reduce, it's going to leave me with 1. So for my vertical asymptotes, I have 2. I have one at x equals positive 2, and then I'm going to have one at x equals positive 1, all right? Which means we have 2 limits we need to, or 4 limits, I guess, but 2 descriptions for each one. So as x approaches 2 from the left, as x approaches 2 from the right, and then we've got as x approaches 1 from the left, and as x approaches 1 from the right. Okay? So those are all the limits that we need. So I'm going to write all those out. Now I'm going to go to my chart. Okay? So I'm going to do one with 2, and I'm going to do one with 1. All right? So the left and the right. This is why we have to be close, because most of the time for 2, we would choose 1. Right? So that's not going to work because that's an asymptote 2. So that's why we have to get really close. So I'm going to do 1.9 and I'm going to do 2.1. Over here, I'm going to do 0.9 and 1.1. All right? So that I'm close, all right, to those numbers that are there. All right? I'm thinking signs, S-I-G-N, what's happening. So if I go back to my original, so let me erase what I, wrote in there so I could see it. Oh, stop it. Okay. Let's go in here and play a little bit. Okay. So 1.9 minus 4, that would be a negative. 1.9 minus 2, that would be a negative. On the bottom, 1.9 minus 2, that'd be negative, but if I square it, it'd be a positive. Okay? And then 1.9 minus 1 would be a negative. So let's think about what would happen if I did that multiplication. So a negative times a negative gives me a positive. On the bottom, I would have a positive times a negative, which is a negative. And then if I divided, in the end, the whole thing would be, dang it. Thank you. All right, see, math. All right, it's hard. Okay, so a positive divided by a positive, I should get a positive. All right, let's see if I do better the second time around. All right, here we go. 2.1. 2.1, plugging it in the original function. 2.1 minus 4, negative. 2.1 minus 2, positive. 2.1 minus 2, positive. Square it, still positive. 2.1 minus 1, positive. Okay? So now I'm going to multiply. A negative and a positive is a negative. A positive and a positive is a positive. Negative divided by a positive is a negative. Woo! Okay, that was a lot of mental math. All right, I may need a snack. Okay, so if we fill in our behavior, to the left, it was positive, so I'd use positive infinity. To the right, it was negative, I'd use negative infinity. Okay, how do we do? Okay. Whew. All right, let's do it again. All right, but this time we're going to use 0.9. Let's see if I do better this time. Okay, no promises. All right, 0.9 minus 4, that's going to be a negative. 0.9 minus 2, that's going to be a negative. 0.9, okay, what's this parenthesis squared always going to be? Okay, shoot, I'm going through fooling with him. 0.9 minus 1 would be a negative. All right. Negative times a negative on the top would be a positive. Positive times a negative on the bottom would be a negative. I divide the two, I'd get a negative. All right, rock and roll. Let's do it one more time. 1.1. 1.1 minus 4 would be negative. 1.1 minus 2 would be negative. I know that first parenthesis on the bottom is always positive because it's squared. 1.1 minus 1 would be positive. Negative times a negative on the top is positive. Positive times a positive is a positive. That's a lot of words. Positive divided by a positive is a positive. All right, I feel like we could win a trivia contest, y'all. All right, so negative infinity and positive infinity. So that should be our results for the aspect. Whew. What questions do you have? That was a lot. You better, Elise, or you still like make it stop?
I don't like to write.
Okay, all right. Well, the good news is we don't have to do it forever, but we do have to do it with these limits, unfortunately. Okay. All right. Well, let's switch gears just a little bit, okay, and look at what we call filling the hole. All right. So you know on that first graph that we saw that had a hole in it, it had an exact location in the graph. Okay. Well, how do we figure that out? We can easily know where it happens in terms of the x value, but how do we get the y value where it's at? Because if I was going to actually graph a function and there was a hole there, I'd have to put a hole. Okay. So I need to know where it's going to happen. All right. So how do we find the y value of the hole? Well, it's really kind of easy, okay? What we're going to do is we're going to actually factor and cancel out the hole. Okay, so if we want to find the y value for the hole, we're going to actually factor everything, cancel out the hole. Okay. And then we're going to plug in, all right, or substitute the x value of the hole into what's left. Okay, so we factor and cancel our whole, let it be gone. And then we're going to substitute. We're going to take that x value where the hole's at and plug it into what's left. All right. What we're doing there is actually evaluating a limit. That's not necessary that you know that, okay? But that's one of the things we'll do once we get to calculus is we'll look at it from that limit standpoint, all right? But the process is the same. We're just going to factor and cancel and then substitute, okay? And it's going to give me that ordered pair where the hole is going to be, okay? So let me show you that one. Okay, all right, and I'm going to show you the limit statement too, so I think it'll make sense why they're the same thing, all right? So let's take our first function. First thing we need to do is factor. What's that numerator going to factor into? -3 and +2, so x minus 3, x plus 2, okay? We want to cancel out the whole, be gone. All right. And then my y value is going to be found where we plug in the value of the whole. So, okay, where is the whole at? Okay, the whole is at x equals -2, right? And so to get the y value, we're going to take -2 and plug it into what's left in my function, okay? So my y value is going to equal -2 minus 3, because that's where my whole was, and that gives me what? -5, okay? So my whole is at the ordered pair, -2, -5, right? That's not difficult, okay? We cancel out, we reduce out the whole, we plug in the x value of the whole into what's left, and that's my ordered pair, okay? Now, the limit statement, this is what this looks like, and I just want to show you this because I think it's going to ask you to write it here in a second, but I want to show you why they're the same. What we're doing is we're finding the y value that's close, okay, or what are those y values getting close to when I'm getting close to -2, all right, because that's where my hole's at, of what's left. Okay, so if you notice, -2 is the whole, x minus 3 is what's left from my original function, okay? To find the value of the whole, or of the value of the y, you plug in that x value, -2 minus 3, okay? So it's the same thing we did without the limit, okay? It's the same thing, you're just plugging it in, right? Just plugging it in. It's the exact same work, okay? Let's do another one together, then I'm going to let y'all try one by yourself, okay? So we want to find the holes. That means I want the entire ordered pair, okay? I want the entire ordered pair. And then we're going to write the limit statement just so you get used to seeing it in case it were to pop up on a multiple choice or something like that, okay? All right. But it's all just substitution, which is kind of nice. Okay, let's look at the first one. Do we have any factors that repeat? X minus 2 repeats. So we know we have a whole at x equal to what kind of 2? +2. Okay. Now, to get my y value, we're going to write that limit statement so we get used to, stop it. So we get used to seeing it. Okay. It's the limit as x approaches the whole. So limit as x approaches the whole. What's left in my original function after we reduced? X plus 4 over x minus 3. And then all we're going to do is plug that 2 into what's left. It's the same math we were doing, just with that fancy limit. Okay? So 2 plus 4 over 2 minus 3 is going to give me my y value. It's going to be 6 over -1 or -6. Bless you. Allergic to rational functions. So the whole is 2, -6. No pluses and minuses on that one, which is nice. Okay, y'all try the second one. All right, step one, we got to factor, right? Because right now they're in that trinomial form, and that's not going to help me. The top one, x plus 7, x minus 2. The bottom one, x minus 5.
So you did the top one.
Did I do it wrong?
That's right.
It's 5, isn't it?
Yeah.
Yep. Appreciate you. Thank you. Alrighty, and so then x minus 5 and x plus 2? All right, perfect. So do we have a whole? Yeah, what's the x value where it happens? At positive 5, okay? So we know it's happening at x equals positive 5. So now let's write our limit statement. What's the x going to approach? 5. What's the function that's left? X plus 7 over x plus 2. And now we're just going to plug in that 5 where there's an x. 5 plus 7 over 5 plus 2, 12 over 7. Okay? Did I do that right? Yep, okay. And so if we do that 12 over 7, so then our whole, the ordered pair, it's okay if we get fractions, 5 comma 12 over 7. Okay, so what do you think about that? Finding the whole, writing the limit. Okay, and I think the writing the limit part would be just in like multiple choice. Okay, you would see that there. Right? But it means the same thing. It's just plugging in y, x for what's left. Okay, it means the exact same thing. Okay, oh goodness. I want y'all to look at these next two. Okay. So on these next two, it says it wants us to write the equation of the rational function with the following properties. Okay. Now, it's given me a bunch of limits, all right? Which means I got to figure out what they represent. What all have we used limits for? We used them for wholes. We used them for behavior around vertical asymptotes. And we used them for horizontal asymptotes, okay? So I think those are the things we're looking for when we look at the limits. Which one are they telling me? Okay. So let's look at the first one. And they're in pairs. Okay. I think this one's interesting. If I'm approaching 3 from the left and the right, I get 5. Anytime you get a number it's a whole. Okay? So if you're approaching a number, so I'm approaching 3, and I get a number as a result, it's a whole. All right? So we're going to have a whole. All right? The x is 3, the y value is 5. Okay? So it's telling me I'm definitely going to have a whole at that ordered pair. Okay? The next pair of limits, again, are approaching a number. Okay, they're approaching a number. And so if they're approaching a number and I get positive and negative infinities as answers, those are vertical asymptote. Okay, so I also have a vertical asymptote at x equals 1. Okay. If it were a horizontal asymptote, it would be as x approaches infinities. All right, so you just got to remember what they look like, each individual limit. All right, so now we want to write an equation. Okay, we want to write an equation. So I'm going to say f of x equals, all right? If I had a whole, what had to be true about the factors of my equation? They were in the numerator and the denominator, and they matched. Okay? So for my whole, that means I need an x minus 3 on the top and an x minus 3 on the bottom. Okay? That's important. All right? For a vertical asymptote, where did that factor have to be? Denominator. Vertical asymptotes fall in the denominator. So if it was 1, my factor would be x minus 1. Okay? Now, life would be really good if that was all we had to do. Okay? Right? It would be really, really good. All right? But we all know that functions could have coefficients out in the front somewhere doing something special. Okay? Funky fresh. All right? It could be a 1. All right? But it could also be a number. So here's what we're going to do. We're going to always put a k up on the top because there could be some kind of coefficient there. All right? And we've got to double check to be sure. All right, we've got to double check to be sure. Well, how do we do that? All right, we do that using that limit process for the whole. Okay, so if we were doing the whole, so I had the limit as x approached 3, okay, and they told me it was equal to 5. All right, so this is the whole. We're going to use the whole to help us figure out the k. All right, if we were doing the limit, we would have marked out the x minus 3's, and what would that have left me with? K over x minus 1. Okay, that's what it would have left me with. If I'd done the whole, I'd have marked out the x minus 3's. It would leave me with k over x minus 1. Okay, now here's what we're going to do. What would we have done with that 3? We'd have plugged it in for x. Okay, so I'm going to keep the k. 3 minus 1 equals 5. Okay, because we know that limit equals 5. They told me it did. Okay, so what's k going to equal? 10. Okay, we solved that equation. K would equal 10. So k over 2 would equal 5, or k is equal to 10, right? So my final equation would be 10 times x minus 3 over x minus 3, x minus 1. Okay, lots of thinking on that one. Okay, that's really understanding what those limits tell me. Okay, that's kind of the top tier problem out of this section. Okay. All right, let's look at the second one. All right, because these are tough. What question do you have over that one? I tried to... Ms. Moore, I have no idea what to even ask. It's okay. We feel that way a lot of times. They feel that way in calculus too. They just look at me and they're like, yeah, I'm not sure what to ask. But we're going to trust. That's what I'm asking for. Okay? That it will all make sense one day. It will all come together. All right, let's look at this bad boy. Because he's got a lot going on too. All right. Okay. So I've got the limit as x approaches negative 2 from the left and the right equals a number. What does that represent? That's a whole. Yep, that's a whole. And it happens at negative 2 comma 4. All right, so we know we got a whole. All right. Now, limit as x approaches negative 1, all right, from the left and the right, and I get infinities as an answer. What is that going to represent? Vertical asymptote. Okay, so I have vertical asymptote at x equals 1. Okay, so let's take that part and let's see if we can throw a function together. All right, so I've got f of x equals, all right, we know we need a coefficient, so I'm just go ahead and put it there. Okay. For the whole, what factor is that going to give me? X plus 2, and it's got to be on the top and the bottom. Okay. Vertical asymptote, what would that factor be? And where does it go? Denominator. Now, I want you to look at this behavior. Most vertical asymptotes we deal with, one goes positive. Yes, ma'am.
Shouldn't the vertical asymptote be negative 1?
Yeah, positive 1. Yeah, it should be negative 1. Yep, I'm a dork. I got the factor right, but I didn't write it down correctly. Thank you. So that would make it x plus 1 down here, right? Appreciate y'all. That's why I have people paying attention. Okay. Sorry. All right. So when we think about behavior around vertical asymptotes, it's usually opposites, right? One's negative, one's positive. What do you notice about these infinities for that vertical asymptote? They're both positive. Anytime they're the same direction, we're going to put exponent of 2 on here, okay? And that's just a weird, funky behavior of an asymptote, all right? It has kind of that even multiplicity because they're both going the same direction, all right? And that's just kind of a thing we have to think about, all right? Okay. So now we got to figure out k. Well, to figure out k, we need to use the whole, all right? So let's think about the limit we would use, all right? We would do the limit as x approaches negative 2. What would be left when we canceled everything out? K over x plus 1 squared, okay? And we know that it equals positive 4 when we're done because they told me it did, okay? Now let's evaluate the limit. Let's plug the negative 2 in. So that's going to give me k over negative 2 plus 1. We're going to square it, and the whole thing is going to equal 4. So we're going to solve for k. Negative 2 plus 1, that'd be negative 1, and we'd square it. Well, negative 1 squared is just 1, so my k is 4. So my final answer, 4x plus 2 over x plus 2, x plus 1 squared. Okay, those are the hardest ones. All right, they're the toughest ones. Okay, last thing. Can we take all those descriptions and draw a graph? Okay, that's the last thing we have to do. Take all the descriptions and draw a graph. Okay, so AP really likes us to be able to work with multiple different representations. Can we take words or symbols and create an equation? Can we take words, symbols, create a graph? Okay, can we take tables and do the same? All right, they like all those representations. So these are our last two problems. All right. So I like this one because it tells me lots of things. It says f of x has a whole at x equals 1. Okay. As x approaches 4 from the left, f increases without bound. As x approaches 4 from the right, f of x decreases without bound. Okay. What's it telling me is happening at 4? It's a vertical asymptote. Okay. So these two tell me that I have a vertical asymptote at x equals 4. All right. So a vertical asymptote, I literally draw a vertical line. Okay. And dot it because I'm not going to equal anything there. That's all that tells me. All right. The other thing it tells me is that I have a hole at x equals 1. I don't know the y value, but when x is 1, I'm going to go somewhere and put a hole. Okay. Now we want to use the behavior around the asymptote. Okay. As this graph approaches the asymptote from the left, it increases. So is it going up or going down? It's going up. Okay, so it's going to go up, get close to my asymptote. All right. It's got to do something over here after the hole, so I'm just going to pull it down. All right. Then it tells me as I get close to the asymptote from the right, it's going to do what? It's going to decrease. It's going to go down. So it might look something like that. Okay. That's all they expect. Doesn't have to be perfect. You got to get the hole at the right x value. Be sure my behavior is correct around the asymptote. All right. See if you can do the second one. He's so loud. If he drops an F-bomb, I apologize in advance. Okay. All right. So we got two holes this time, one at -2 and one at +3. So I'm going to go in there and draw those bad boys at -2 and at +3. I'll put that one right here just for fun. All right. Then it tells me as x approaches -1 from the left, it's going to decrease. As it approaches -1 from the right, it's going to decrease. So this is a vertical asymptote. Okay, at x equals -1. So let's draw that bad boy in. Okay, so if I come from the left, it's going to decrease. So it's going to go down. Oh, I didn't want to pick yellow. It's going to go down. Okay, it needs to do something, so I'm just going to have it do that on that side. Okay, and then as it approaches from the right, it decreases. It's going down again, and I'll let this one kind of go this way, and there we go. All right, I could have made that turn down again. All right, doesn't matter. As long as it's doing what it's supposed to close to the asymptote. Question about that? Okay, so I think these are better. Example 4 were the toughest ones. Okay, were the toughest ones. All right, so lesson practice. All right, you got 2 worksheets, worksheet A and worksheet B. All right, on worksheet A, so this was 2 sections, 1, 9, and 10. Tomorrow we're just doing 1 section. Yay! All right, I want you to look at 1, 3, 5, 6, 8, and 11 on the first one. And then on B, 1, 2, 3, 4, 7, 8, and 10. And just because of time, no wrap up today. Okay. I'll take that off. It's on there, but don't worry about doing it. Okay. Yeah. So don't worry about your wrap up today. Okay. Good job. All right. Practice this a little bit. You're going to need it, right? So tomorrow we're going to do 111. If you've looked at the calendar on Google Classroom, I went ahead and did some advanced planning. Next week's all the way planned out. I'm going to be out Wednesday of next week to go to my best friend's son signing his letter of intent to play football at college. So I'm going to Smyrna High School to watch him sign. And because she's going to be at Cheer Nationals, so she's not going to be there. He's going to Center in Kentucky. He's really excited. So he got an academic and an athletic scholarship. So yeah, he was really excited. He's got some kind of something. He's going to be a physical therapist. Like, they go ahead and they put you in touch with their alumni that are in the general area and all this stuff anyway. So he's got that tonight. So anyway. But, okay, you can see when the test is probably going to be for this second half of this unit. I went ahead and just tried to pre-plan. If it's not bold, it's not official yet because life happens. If it's bold, it's what we're doing. Okay? So there you go. All right? So do a little practice tonight. We got about 8 minutes left, and I'll see ya tomorrow. And it's Friday. It's Friday. Are you going on a field trip tomorrow, JJ, or no? I can't remember. Tomorrow's the 31st. Oh. It disappeared. Is it under my feet? Oh, no. So you can see how level the floors are. It went a long way.
It's still going.
It's still going.